Okay, first problem is just take these 3 points and see what it takes to fit them to the equation y equals ax squared plus bx plus c. And let's just review what we did last time, and I think everybody did pretty well with this, or at least I haven't looked thoroughly, but I think for the most part people were doing pretty well here. Okay, so what do? We plug in the x coordinate of the first point and the y coordinate. X coordinate is 2, so x squared is 4, so ax squared would be 4a. Bx, x is 2, so that would be 2b. And c is just c, and y is 4. We do the same thing for the other 2 points. 0, 5 is going to give us c equals 5. Negative 1, negative 12, the y is going to be negative 12. X is negative 1, so x squared is 1, so we just get a. X is negative 1, so we're going to get negative b, and of course we're going to get c. Now, I create the augmented matrix, and there's no reason to keep the equations in the, to do the augmented matrix in the same order we have the equations. We just have to be sure we get all 3 equations. So I choose to put the third equation first, because I'm going to get a 1 here, and that 1 makes it easy to get my zeros here. Now I'm assuming everybody is completely comfortable, or at least competent, with reducing a matrix. Okay, we've been doing that for a week and a half now, and I'm assuming everybody's good with it. So I'm not going to talk about how to reduce the matrix, just talk about what happens depending on what you get when you do reduce it. Okay, well, second row, well, actually I want to put the c equals 5 in the third row, because I know now when I reduce a matrix I want to get zeros, 2 zeros to start my third row. Of course, if I have a matrix of this size. So my c equals 5 becomes that row, and that row's already reduced. We don't have to do any more with it. And then my remaining row I'm going to put here. That's going to be very easy to reduce this. We subtract or multiply the first row by negative 4, add it to the second. I'm going to get my 0 here. And then we're going to divide by whatever number we have here through this row, and we're going to get a 1 here. And then if we choose, we can wipe out the constants above this 1 and the constant above this 1. Again, in a process that's very familiar to you. So the basic idea is we just get this, and if this system reduces down to where I have a 1 here, a 1 here, and a 1 here, I'm going to have a solution. Whether I take it past the upper triangular form or just leave it in upper triangular form, I'm going to get a solution, and my equations are in the variables a, b, and c. Of course, I wrote x here because I was talking about x, and my increasingly feeble brain kind of picked that up when I was writing it. Anyhow, you got to watch me. So our variables here are a, b, and c. Our solution, as you can tell, is going to give us values of a, b, and c. And we're going to be able to put those solutions into this equation and get our specific quadratic function, which we can then graph and verify that these points lie on the curve. And that will be the case. It will be the case any time for any 3 points, as long as no 2 of them have the same x coordinate. Because, of course, if 2 points have the same x coordinate, that means one lies directly above or below the other. Well, certainly one of them lies above one. Well, anyhow, yeah. They lie on the same vertical line. And the solution would then fail the vertical line test. Well, if we have a solution for a, b, and c, we get a function here that is a function, and it won't fail the vertical line test. So if we had the same x coordinate for 2 points, we would not be able to reduce this to the point that gives us a solution to the system for a, b, and c. Okay, so you can check that out. You'll encounter that, but I kind of want to warn you on that. Okay, well, that's pretty much our situation anytime we're trying to fit points to a polynomial. Okay, now we're going to go on and do one where we have 4 points. And so you might think about what differs if we have 4 rather than 3 points.